industry, you will find that resistors are not called resistors. They are called CFRs, MFRs and WWRs. Now a CFR stands for carbon film resistor and an MFR stands for a metal film resistor. When you think of a film deposited over a non-conducting part, and on this film a ribbon is cut. The closer the ribbon, the higher will be the resistance, and the further apart the parts of the ribbon, the lower will be the resistance. We call this pitch. By controlling the pitch and the thickness of the film, we are able to get very accurate values of resistors and a very large range. The range of carbon film resistors and metal film resistors is 0.1 ohms to 10 mega ohms. You can also have a wattage right from 100 milliwatts to 2 watts. The other most popular form used is the wire wound resistor. As the name suggests, wire wound. Wire is being wound over something. We use a resistance wire. Why a resistance wire? Because many wires change their resistance with temperature. You want an element which does not change so much with temperature, which does not change so much with time, and yet can give you a good range of resistance. To make the resistor, the principle follows is the same. If you increase the pitch, take fine wire and wind it very closely, you will get a high resistance. If you wind it more far apart and with a thicker wire, you will get more wattage but lesser resistance. Wire wound resistors typically range from 1 watt right up to 200 watts or even 500 watts. So they can dissipate a lot of power. The other commonly used form is the thick film resistor. These have become very popular because of their small size. Let's look at their size. We refer to them many times as 0603 or 0805. Now what does that mean? The length and width is 0.606 inches by 0.03 inches. They consist of metal oxides, and by laser cutting these films we are able to get very accurate values, and again a very large range of values. However, wattage is a constraint. You can't have very high wattage. Typically they are in the range of less than a watt. So there are different kinds of resistors used in industry. They all have their own functions, their own ranges, and you need to decide what you want based upon the application. Let's say your friend comes around and says, hey, I'm looking for a supply of 44 volts. Have you got something? And you say, yeah, I've got a 100 volt source actually, but I made a voltage divider and you know, here it is. He says, fine, okay, great. So do you have 44 volts from it? He said, yeah. But it also has a resistance in series, which, if you remember, you know what? Thevenin's theorem. We use Thevenin's theorem. What do? We short the power supplies. And when we short them, you get these two resistances in parallel, which gives a resistance of 12.32 kilo ohms. So the Thevenin's equivalent circuit of this becomes a 44 volt supply with a 12.32K resistor in series. Your friend comes along and says, hey, great, you have 44 volts, but I don't believe you are. Let me check. And he takes a voltmeter and checks and he says, wow, it's there, almost there. And he's very happy, you're also happy. But let's see how long this happiness lasts. So your friend takes the voltage divider from you and he puts a 1K resistance load. We shall call this RL. And let's see what happens. Current is now being drawn. But the voltage which is left across RL is very much different. He again puts a voltmeter and he says, hey, I got only 3.2 volts. What happened? You told me 44 and you're giving me 3.2. Why? You know why? Because he has stolen the voltage. I call this Thevenin's thief. What does Thevenin's equivalent resistor do? It steals the voltage. You have 41 volts falling across the Thevenin equivalent and only 3.2 volts left. So what is left for you to do now? For your friend, he has only 3.2 volts. Now you have to be very careful about Thevenin's thief. We're going to design voltage dividers to overcome Thevenin's thief. We're going to see in the next few slides. Before that, I tell my friend that, hey, I made a mistake. This divider will take only a 1 mega ohm load, and it should be okay if you put a 1 mega ohm load. So he says, okay, let me try. He again puts a voltmeter. He puts a 1 mega ohm load, and you see that you have almost 44 volts. How was this happening? Once again, voltages are being divided. They are being divided between Thevenin's equivalent and the load. First, with 1 kilo ohm, you had almost 1 over 1/13, or 1 over 13, that is almost 1/13 of 44, which gave you about 3.2 volts. And with 1 mega ohm, you have 1000 over 1012 into 44, which is almost